Okay, the Western United States is a very tectonically, let's say, complicated part of the world. There's a lot of different layered things going on here. I think that claim should ultimately make sense because when you look at the Western United States, you're very struck by how just much mountain activity there is here. All of this part here is a series of orogenies and floods and collapses and strange intermixing tectonic activity. No such complexity exists in the East. Here, the land is old and simple, eroded and low lying. But here in the West, there have been a number of events which have formed extravagant mountains, some of the tallest in the world, the tallest in the continent, certainly. Although, of course, these ones are pretty tall as well. Um, so, I came upon this map. I just went to Yellowstone for the first time. I came upon this map while I was reading about this. I don't really know anything about geology. Well, I have I have never studied geology. Uh, but I wanted to try and understand why the continent looks like how it does, basically. My brother asked a pretty wise question, which is the Rockies are all over here. Uh, you know, the Rockies are not where the coastline of America is. But if mountains are formed by subduction, how did this happen? How did these Rockies actually form here so far away? Uh, which led me to a series of revelations which have helped me better understand how all tectonic activity works, and gotten me quite interested in geology recently. So we're going to go in temporal order. The first question is the Laramide orogeny. How did all these big mountains come up? I like this. I think this is a pretty good depiction. It's not wrong to think of the Rockies as being formed through this. Okay, so they formed through this event, the Laramide orogeny. Let's write this down. This was 80 to about 40 million years ago. Laramide orogeny. And an orogeny is an event that creates mountains. The Laramide orogeny was caused by this old plate that basically doesn't exist anymore, the Farallon plate, subducting underneath the North American plate. Well, that makes sense. That's how most mountains seem to be caused. So, we can think about it like this. This swath of the American continent was basically not here yet. It was later accreted and added on through activity. So the coastline, we can imagine being on the far edge of this, the inland edge of this kind of polygon that I've drawn. But that still places the Rockies notably far away from the coastline. So something else weird is happening here. And that is this. The Laramide orogeny was a basically. Hang on, let me draw this out. Oftentimes, when subduction happens between an oceanic plate and a continental plate, the oceanic plate goes way down because it's heavy. It's made of this big, heavy rock, and these continental plates are so thick and big, and these oceanic plates are simply much thinner. So the oceanic plate plunges underneath the continental plate and then melts and comes up in the form of volcanoes and mountains. we come back to this as an idea because this will be relevant later. But the Laramide orogeny was unique in that it involved because of some reason which I don't fully understand, to be honest, the Farallon, the oceanic plate, subducted at a much more shallow angle than a plate might usually do, and did not plunge into the earth and melt as is happening, say, in the Andes, or as is happening now in the Cascades. Instead, it pushed under at this shallow angle and led to all of this rock across this huge swath of land getting shoved and cracked upwards. So let's imagine it like this. And there is some volcanism, there is melting occurring, but it's across a big area. But many of the most notable mountains in the Rockies, one of the most notable ranges along faults, were not even caused by volcanoes. They were caused simply by this plate underneath pushing up this continental plate, and thus leading to the sudden creation and bending and folding and breaking of land, because now there's basically two plates in the place of one. So imagine this is our Laramide orogeny, and it is this old oceanic plate that is mostly gone now, the Farallon plate, subducting under at a shallow angle the North American plate. And this is happening for millions of years. When I mean millions of years, I mean like 40 million years. Like, the Laramide orogeny was going on for from the start of the orogeny to, let's say, the end, is the same amount of time from the end of the orogeny to now. So a long, long time that this was going, which is why this is also such a widespread and physically lengthy amount of mountains that have been formed. And then sometime 30 million years ago, the Laramide orogeny begins to slow and end as our old friend, the Farallon plate. The Farallon plate is, I wish I could write directly on this. Oh, hang on, there's a way I can. We're going to do that. Never mind my poor video editing skills. Okay, the Farallon plate is shooting this way, and that's great. And the North American plate is shooting this way. Okay, green was not the right color choice. The North American plate is shooting this way. And that's great too, which leads to a lot of subduction and the formation of the Rockies, like we mentioned here. But it's doing this for 40 million years. This plate is moving a lot. It's going to keep moving. And this plate's moving a lot. It's going to keep moving. So 40 million years go by, the Farallon plate has pushed itself to the far edge of North America. And this section, which is so very tiny here, because this is way long ago, this is like 80 million years ago that this image is trying to show. This section started as so tiny here, this tiny spreading ridge between the Pacific and the Farallon. Well, this spreading ridge has also been moving towards North America over the span of these 40 million years. And, well, 40 million years go by. Suddenly the spreading ridge is right around here. And then, sometime around 30 million years ago, the spreading ridge slips under North America and subducts, like the rest of the plate had done. But here's the problem. When the spreading ridge is where the plate is growing from, where new plate is forming. When it's underneath the North American plate and melting, well, suddenly there's no space for the Farallon plate to be forming anymore. And now suddenly this tiny little plate here has migrated all the way over here and is now pressed up against the edge of the continent. So hang on, we can go back to our image here. This gets us a little bit more temporally relevant. So, the Pacific plate has different ideas. the Farallon plate was moving this way. But the Pacific plate is really not doing that. The Pacific plate is really actually trying to rock like this. It's swinging that way northwards, and it's creating all this volcanism in Alaska and the Aleutians and in Japan. But the disappearance of the Farallon's sudden and violent eastward movement ended the Laramide orogeny entirely, and instead brought a new kind of fault line up against the western continent, the western edge of America, which is this kind of transform fault, as is labeled here, transform. So let's add this to our timeline. 30 million years ago, the Farallon breaks up. I don't really think we have space for an image there, and maybe we don't even need it. In time, as a direct effect of this Farallon plate breaking up, we now have this transform fault. This transform fault here. And that is not mountain forming. So this is doing two things. One, instead of subducting, pushing up new mountains, it's now kind of allowing space for deformation and sinking, and it's almost kind of pulling some of these mountains, especially from the southern end of the Basin Range province. It's pulling them north, and it's pulling them apart. So Farallon breaks up as an effect. San Andreas transform. The other thing that I was really struck by when I was in Yellowstone is the Teton mountain range, which I went to go see, which is not in Yellowstone, but is right next to it. The Tetons are absolutely unbelievable. I mean, hang on, let's zoom in on them. They are so pointy, and they are so tall. Here they are. You really can't help but wonder what made this perfect little straight line of tall, pointy mountains. The answer is this. Once subduction ceased, a new force became the present and the prevalent kind of acting motion on this part of the continent. So imagine this. All of these plates earlier into the Laramides are pushing up. There's all this rock, there's an oceanic plate down here, and there's all these new pushed up rocks, and this plate is really thick. It's way thicker than the rest of Earth. And all the force that was making it stay thick, that was shoving them together, is now gone because the Farallon is disappeared underneath the continent. Well, that means that all of this, imagine you stack up a big bunch of bread dough, and it's a big pile. Well, if you stop working it, the dough just wants to sink down. It wants to spread out. Gravity wants to do its work and make things flat. So suddenly, let's say 20 million for honestly the next several million years, but let's just say 10. Although in some sense this force is still going on, but not quite as exciting now. The this kind of divergent force begins, and the western part of the continent begins splitting. It begins sinking and pulling apart from all its height that was earlier built into it by the Farallon. And that is this basin and range province. So, basin, 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 and range. And we should get a little drawing for this, because this is an important one. So, to indicate this drawing, let's first look at what do we have with our layer meteorology. All of this land is built up. So here's our plate. It's got all these mountains on it. And these mountains are undergirded by even another continental plate. So now they want to sink down. They want to spread out. And in some cases, such as, say, the lovely Teton Range, which is the farthest eastern reach of this basin and range activity, the spreading activity, what is happening is basically this. Here, let's take a cross-section of the Tetons. Okay. As all this land is spreading down, this part is sinking, and it mostly is sinking. Jackson Hole, this big, deep valley that gets really cold because it's a hole in the mountains, is actually much larger than the Tetons. It is really the effect of the Basin and Range province. But part of all that slipping down is suddenly there is space for the mountains to be, the rocks to be correcting and being pushed up in some places. So imagine, I saw a great diagram of this and I wish I had it on hand. Imagine it's basically like this. As these are going down, well, this section is naturally going to get pushed up. And it's not because there's tectonic forces shoving on it, it's that just all this mass, this rock, which is big and crushes and crumbles around and causes earthquakes if it moves, is sinking and deforming like bread dough. But it can't do it so smoothly as bread dough can, so uniformly. So as it begins to sink and smooth, it also crumbles and cracks up in different places, and it spreads out, and some of it sticks up, and a lot of it spreads out in these big valleys. And, you know, this Basin and Range province, it's indicating here Nevada is really what's been affected. But even it does indicate the far end of the Tetons in Wyoming. But if we come and zoom over at Nevada, this effect becomes a lot more clear. Like, look at these series of valleys. Valley after valley with tiny little mountain ranges separating them. It's that same effect that created Jackson Hole and the Tetons. So, the Basin and Range is now the main acting force. And it's like that up until very, very recently. And it still is, in some sense, the acting force. It's just not quite as violent anymore. Since then, there has also been some... which one do I want to talk about first? Okay, we have to talk about this other thing first, which is Yellowstone itself. Yellowstone, it's a hot spot. And when we think hotspot, we should think. Hang on, I'm erasing this. We should think what that means is it is a large swath of land where some kind of plume of magma has arrived underneath it. So there's the heat of the mantle has been pushed up higher. I don't have too much space here, but we can still draw to indicate a hotspot. You know, the Earth is, well, actually, let's just find a hotspot. I bet there's a good image we can find. Yeah, this is pretty good. This is Hawaii, which is also a hotspot. So no one quite knows, because we can't really go into the mantle. We've never developed that ability. The farthest we've gone down in the Earth is actually surprisingly not very far. The Earth is really, really big. But the leading theory is that there's these things called mantle plumes. So some kind of hole, maybe some tectonic activity is creating it, maybe some weird convection in the mantle is creating it. And this little stream of hot magma is shooting up from the edge on the core, way, way down where it's really hot, all the way through the mantle, and it's hanging out at the top by the crust. And up by the crust, suddenly all this stuff is really hot. Magma up there is usually not quite so hot. So this hot magma is beginning to build up, it's beginning to melt the crust, it's beginning to interact with the forces around there, such as water, which obviously is very prevalent in Yellowstone. Or in the case of Hawaii, it's melting the crust to create these series of shield volcanoes. In the case of Yellowstone, it's doing two things. One, it first did something really, really remarkable, which is, let's write down, 17 to basically 16 million years ago, basalt floods. So, this plume shoots up through the Earth, and we're like, wow, this is interesting, it's getting hot. Then suddenly, it's melting, and it's trying to break out. It's really high pressure. It wants to be up at the top. This remarkable event happens where all across the Columbia Plateau, hundreds of fissures open in the land. Let's just start imagining these fissures. And from these fissures pour out just a huge amount of lava, of just hot magma directly onto the surface of the Earth. And this basalt floods. If you go to Eastern Washington now, you can see where these basalts have laid up. And it's huge. It's a big, thick layer of basalt. And over the span of probably about 1 or 2 million years, these fissures are just pouring out lava all the time. And in doing so, they are covering up a lot of the old rocks around here and creating this strange effect, which is the Columbia Plateau now. The plateau is now higher than the rest of the surrounding area. The plateau is also clearly the effect of basalts, because you can look around and see these basalts. They're stacked, and they're kind of hexagonal grids. I bet if I just zoom in on a random place here, let's see if we can see any of these, because maybe we even can. Should be really exciting. Oh, but maybe not. Okay. There's too many sedimentary rocks here for Google Earth to be able to pick up such fine details, which I suppose I should believe. Okay, indeed. It's all covered with sediment now. Well, according to the satellite. You can see these if you get closer to them. But this Columbia Plateau, you can see it. Here it is, this strange space where it's less forested, it's higher up, and it looks kind of barren and dry, but it's also not mountainous, unlike so much of the surrounding area, because it's been flattened out. Lava flows like this are uncommon on the surface of the Earth, but when they happen, they are smooth. So, Columbia Plateau, mantle plume, creates all this activity, pours out all this magma. The mantle plume has probably exerted most of its heat and its basaltic lava, but there's still the plume itself, this narrow little column. It had been moving all this lava up to the surface for a while, and simultaneously in a big event in a narrow time span, a lot of that poured out. But the plume remains, and the plume remains in the form of the Yellowstone hotspot. So the first Yellowstone eruption happened here around 13 million years ago. And since then, there have been numerous others, about every 600,000, or let's say roughly, years, as the North American plate has been moving. Hang on, which direction of movement makes sense? I think I want to say the North American plate is moving this way. Yes, it has been. So it started here, and the plate has been moving over this plume, which started here. And now the hot spot has ended up here. The hot spot, we can try and draw it a little bit, is this plume of magma coming up to the top, and it's kind of built up near the surface. The surface is just chilling out here. People say that Yellowstone is a supervolcano. What is a supervolcano? A really big volcano, basically. Maybe not quite well defined. There's some extravagance to claiming that things are super anything. But it's an exciting idea, and let's say it's a supervolcano. It does have really big explosions because the plume is doing a similar thing to what it used to be doing. Actually, though, it's now rhyolitic, but I don't understand rocks enough to talk about those things. It has formed a series of calderas along the Snake River Plain. And it's formed a caldera. A caldera is a collapsed kind of crater, basically. Crater lake is a caldera. All this magma builds up here at the top. And then finally, okay, the magma has the chance to shoot out. It says, let's explode in various directions. And we're freed, and ash is coming out this way, and pyroclastic flows are coming out this way. The ground is literally bulbed up where the magma is pushing against it, and that's all well and good. And now, well, the magma has all poured out. There's now just a narrow little plume left, no buildup at the top, there's no head, and all the magma is gone. So this bulge that the magma caused can't be sustained. There's nothing pushing against it. So instead, it collapses. And this collapse forms a caldera. The effect of this caldera is that all of this geothermal activity is closer to the surface in the caldera than it is in the rest of the continent. And it also is a collapsed space, a large collapsed space. So let's go back to Google Earth. I was really struck when I learned this. The Snake River Plateau, if you follow the Snake River, hang on, let's pull up. There's another great type of map I should have here. Saturated relief map of the U.S. This is a nice map. Well, one, look at just how mountainous the West is. This is what I'm saying. What happened to all these events? look at the Snake River Plateau. Here we are. See how flat it is. There are these series of wide, flat arcs, and I was always like, I wonder why that's there. I guess just the river must have caused that somehow, because, if you look at the Columbia, basically the same thing has happened. And actually, that thinking is not wrong, but it has nothing to do with the river. It has to do with the fact that these calderas, these explosions which forming these calderas, happened all the time. And they happened in a basically straight line across the plateau, which made this area, oh no, not this one, which made this area big and flat. So now the Snake River Plateau is a big flat place where the river sits right on top. It's very good for farming. And right at the very end of the Snake River Plateau is what is now Yellowstone. Yellowstone is here. This is the caldera. So you can really see how it's just the most recent in what have been numerous other eruptions in the past. So that brings us to Yellowstone, and underneath Yellowstone we have this most recent of calderas. All of this heat is built up here, all this magma, this plume is still here, the earth is thin, so we get a lot of exciting little things like geysers, bursting out little geysers, and we get little hot springs welling up in different places, and we have this very striking kind of alien environment that Yellowstone forms with its geothermal activity. And so that's bringing us most of the way up to the timeline. These Yellowstone eruptions started 13 million years ago, and they have been continuing since then. So we just talked about Yellowstone a lot. Let's get it on our timeline. 13 million years ago. Yellowstone. We'll just say Yellowstone, because there's so much you could say about what Yellowstone is, but it is Yellowstone. So, finally, we want to understand what is going on with the western part of the continent. We understand the Rockies, we understand the Basin and Range Province, we understand the Laramide orogeny, the Columbia Plateau. The far west, there's two other things happening out here. This is where I'm from, Washington. It's very obvious that there are two, they look actually, like, to me the same, but they actually are two different things. There are two mountain ranges, and they're really tall. And I haven't really been to the Rockies aside from this Yellowstone part. I haven't been to Colorado or whatever. But I've been to Mount Rainier, and I've been to Mount Baker, and I've been to Mount St. Helens, and I've seen Mount Hood up close, and the Three Sisters up close, and they are all volcanoes. Most of this, even Yellowstone isn't really a volcano. Yellowstone's really a caldera and a hotspot. They are all volcanoes. They're stratovolcanoes, which means that they are formed from repeated eruptions. Things keep blowing up on their side and blowing up and blowing up and blowing up. And with that effect, they become tall and reaching. And you look at Mount Rainier and you can see how it's the effect of repeated eruptions pouring lava flow after lava flow onto each other. Mount Rainier is a huge mountain. What caused all these volcanoes? Why are they here? Why are the Rockies not volcanic? Well, we already talked about that latter question a little bit. The Rockies aren't volcanic because subduction for them has stopped. Because the Farallon plate, I said, was destroyed underneath the North American plate. But I actually kind of lied. The Farallon plate was not entirely destroyed because this thing, the Huanghe-Fuca plate, actually is just the remnants of the Farallon plate. Most of the Farallon plate, that's why I wrote, it breaks up. Most of the Farallon plate is indeed gone, and it's certainly not growing very much anymore. But a tiny little amount of it is growing in various other places. Some of these plates further south in South America, the Nazca Plate, are also remnants of it. But the Juan de Fuca Plate is the most notable one here. And the Juan de Fuca Plate is the only place in the western, lower 48, where subduction is still happening. And because of that, it's also the only place where this chain of volcanoes exists. See how they end right here? There's none south of here. Even the Sierra Nevadas, which are very tall, don't have volcanic activity going on in them. So, a lot of these volcanoes are even still really new. Mount St. Helens is really maybe 20,000, 30,000 years old. Mount Rainier is only a few million years old. So let's write, really maybe we could write 5 million to understand how the current cascades look. 5 million years ago. Cascades. Cascade volcanoes. We'll say cascade volcanoes. This mechanic was the first thing I talked about in this video, which is the simple, common way that happens when oceanic and continental plates interact with each other, which is that they run towards each other, and then one of them hits, and the oceanic plate usually plunges underneath the continental plate, way, way under. And it goes deep under, and then it starts melting, and it starts coming back up. And as it's coming up, it forms little volcanic peaks. This is exactly what's happening with the Juan de Fuca Plate, just like the Farallon Plate, because it is the Farallon Plate. It's plunging underneath this little section of North America, and as it's getting just a little bit deeper, past the shelf and past the coast range, it's melting, and it's coming up in this pretty clear line of volcanoes. Which is now the Cascade Range. These are active. This subduction is happening right now. The volcanoes, the Cascade volcanoes, are some of the newer volcanoes in the world. Mount St. Helens erupted just in the 80s. Pretty notably, a lot of it blew up. It's much smaller than it used to be. Mount Rainier very well could erupt again, and has erupted several times within the past 100,000 years. The other effect of this subduction is the ever-famous and worried about, at least in the Pacific Northwest, the Cascadia subduction zone, which is happening right here. And what's happening there is, again, this plate is plunging underneath, and the subduction zone is the potential for the continent on top to suddenly shift upwards as this is pushing and moving about. Sometimes in large movements, the continental plate thrusts upwards. It's called a megathrust earthquake. And the largest earthquakes in the world are megathrust earthquakes, and they only happen in ocean trenches like this. And here is one of them, right off the coast of Washington State, causing all these amazing volcanoes that we can see from even our windows every day. If it wasn't so smoky outside, I could see Rainier. But it also puts us in perennial danger of these huge earthquakes. And so that is the effect of this remainder of the Farallon Plate, the Juan de Fuca Plate, existing and pushing under here. I feel like it would be cheating if I didn't just finish this video out with talking about what are the coast ranges. And I understand that a little less better, which is why I haven't talked about it yet. But let me essentially say that the coast ranges are caused not by volcanoes, but rather by the plates movement, the oceanic plate movement, what's called accreting new land, just right on the side. So let's look up tectonic accretion in the coast range. I'm sure we could get a nice little visual of this. Here it is, exactly what I'm looking for, the Oregon coast. So, the Juan de Fuca is pushing under, but with it, it's bringing all of these It's bringing island arcs. It's bringing plateaus of lava from the ocean. It's bringing chains of volcanoes from the ocean because it's been doing this for, well, we're now 80 million years since the Farallones started subducting. It's been doing this for 80 million years. There's been constant movement from the ocean, from the Pacific, shoving all of this stuff under and into North America. So because of that, the western coast of North America has been constantly growing. It's been accreting new land. The effect of this land, the most obvious one, is the Coast Range. In Oregon, the Coast Range is very slim. It's not very notable at all. Um, it's these low mountains. You have to drive over them to get to the coast, so it's always kind of like an experience. Um, it's not too dissimilar in California, I believe. Okay, it's a little sharper up here. Um, we don't want to go too far south because we're going to enter a different province if we do so. But it's quite notable in some places further north. The Olympics are actually, pretty sizable mountains. I was just here. Where was I? I was just right here. Oh, yeah, actually, I think this is the exact place. Wow, isn't that amazing? Yes, I was just right here in the Olympics, which was really the foothills. But I've been up higher in them, and you can tell they're big, tall mountains. There's constant glaciers on them. The mountains of Vancouver Island itself, of course. And these are not caused by volcanoes, but they are caused by the plates moving towards, there's a little, even an underwater, a seamount arc on the ocean moving towards this big continental plate. And it's going to hit it, and this part's going to subduct. But all this is going to be pushed into the side. And it's going to build up on the side in what's called an accretionary wedge. So now you've just kind of wedged all of this rock to the continent. And in some places it's more obvious and sharp, and in some places it's less. But the Olympics are formed by a totally different process than the Cascades, which is a totally different process than what made the Columbia Plateau and Yellowstone, which is a totally different process than what made the Tetons and what made the Basin and Range Province in Colorado, or well, not in Colorado, in western Utah and in Nevada, which is not totally, but a different process that made the Rocky Mountains so far away from the coast. And so here it is, all of the explanations of what is happening in this photo, and what is happening in the Pacific Northwest is, I guess, what I really wanted to talk about, because that's where I'm from. It's a crazy story, and learning things is really cool.